Oh, okay. So with observations over the ocean, there's a couple of problems. High costs in installation and maintaining those observations, and that's due to the fact that the ocean's a pretty brutal place and that seawater is corrosive. So that combined with large distances that you're going to need to travel to maintain those installations, and the multiple man hours that it's going to take to do that maintenance after that travel, presents quite a few challenges for gaining observations over the ocean. Okay, so at the surface, there are a number of existing or traditional observation data sets. So the first is the set of meteorological variable instrumentation sets at in the on buoys over the Pacific. I mean, over the entire world. So here on the left-hand side is a map of the buoy locations that have meteorological sensors in the Pacific Ocean. And so you could see this leaves a huge area of the ocean unobserved. And that's because buoys are going to generally be relegated to coastal environments due to the fact that they are moored, so the ocean can only be so deep. In addition to the fact that to maintain those observations, you're going to need to travel to them. So that's a big part. So that data set is complemented by the large data set that we get from maritime traffic, from ships of opportunity, which are basically just maritime vessels that are fitted with sensors. So they're great, but they do generally retrace well-traveled routes, and they have, and to some degree they'll avoid bad weather for good reason. But that does leave us with the absence of observations in sometimes the most important area to have those observations. And so on the right-hand side, I'm just showing a plot of 24 hours of maritime traffic from satellite AIS data. Jack, did you want to add anything about surface observations?
Yeah, I was just noticing that the buoy one there on the left it's just keep that in mind when we do the validation study, because we compare it against buoys, and you can see the distribution of buoys are primarily on coastal regions, and especially in North America and in the tropical Pacific. So just keep that in mind when I show the validation results, that we're not sampling the full ocean necessarily, because we are comparing against buoys, which are fairly limited in, as you said, location.
Yep. Yep. Yeah, and all those red dots are actually stations where they're no longer collecting current observations. They've gone down for one reason or another. Let's see. Okay, so the problems at the surface are one thing, but they get a lot worse when you go to collect observations above the ocean surface, through a larger depth of the atmosphere. And so here shown on the right is a plot of all the upper air locations across the whole world. And so at these sites, twice a day, an expert will launch a radiosonde. So a radiosonde is just like a sensor package attached to a high altitude balloon. And again, that has to be manually launched by an expert. And so the key thing that you'll notice in that plot is that there are no upper air sites over the ocean, for good reason. But so that does leave us with huge gaps in the the ability to sample the atmosphere vertically. Those observations are complemented by aircraft traffic, which is often fitted with meteorological sensors. But the issue with those is that over the ocean, predominantly they're going to be at cruising altitude, so that leaves much of the depth of the atmosphere unsampled. And so finally, we do have satellite microwave sounders, which do record temperature profiles through the atmosphere. But they themselves are going to suffer from issues of coarse resolution in the horizontal, and even maybe more importantly, coarse vertical resolution. Again, Jack, did you want to add anything?
No, I mean, one other thing that you don't cover there is, at least in North America and the US, they do have wind profilers, which are land-based profilers, which do sample the atmosphere more frequently than twice a day. Again, somewhat the resolution issue. At least they have a high time resolution. Again, with time resolution too, is this question of where you do the observations. Your radiosondes are typically twice a day. Satellites are when usually the overpass of the satellite is, so they're fairly, again, the sampling rate is fairly low. So these are problems that you have to deal with getting observations, especially over the ocean.
Yeah, yeah. Yes, indeed. Okay, so, oh, don't go past this one. Great. So these gaps in observations are gonna produce a certain problem, and that is because numerical weather prediction is an initial value problem. And what that means is that the errors that exist in initial conditions are going to be the predominant source of forecast uncertainty. Not only that, but the errors that start out are going to grow over a forecast and they'll propagate downstream. So errors that exist at one point over the ocean will eventually propagate downstream so they're affecting forecasts over coastlines and over land and et cetera. And so that's all important because global weather is interconnected. So an error in one place is going to result in an error at another place. Did you want to add anything, Jack?
Yeah, plus that's going to affect the quality of the forecast as you go on. Yep.
Right, right, right. Yeah, right from the initial point. Yep. Okay, so how we're going to solve this problem? Spire RO in this role can fill a key void. So just to quickly explain what RO is. So the idea is that radio occultation measurements are obtained by analyzing the degree to which GPS signals that are passing through the Earth's atmosphere are bent, when they pass through the atmosphere. Using that information, Spire is able to gather profiles of temperature, humidity, and pressure through a large depth of the atmosphere. Right. So importantly, every day, Spire is collecting 10,000 of these profiles right now. And this results in a homogeneous, unbiased data set that is able to cover the entire planet all the time, which is in contrast to something like the radiosonde network, which is going to launch twice a day. So that continuous nature of the radio occultation data set is going to be extremely important to covering some of these gaps that we've been talking about. Okay, so here I'm showing two examples of Spire RO profiles at two locations that are quite close to each other and only a few moments apart. So both of these are compared with the GFS model profile in green. And so there's two key things I want to highlight here. First is that these examples illustrate the fine vertical resolution and high quality of Spire's RO observations, and that they extend through a huge depth of the atmosphere. And second, I would like to point out that the GFS model atmosphere at this point is much colder than we've observed in the Spire profiles. And that's through a huge vertical depth, right? And so this error is going to have consequences that extend past just here and will extend down to the surface, where in fact in this location, we noted that there was a sea level pressure error of over 10 millibars. And so for anyone in maritime weather, a error of 10 millibars at the surface is going to produce quite a difference in the wind forecast at that point. Did you want to add anything, Jack?
Yeah, I mean, 10 millibars would be a huge error. Even a
Yeah.
couple of millibars would be a large error particularly
Mhm.
for winds.
Yeah, exactly. Yep. Right. Okay, so keeping in mind the quality of the observations being collected using RO, here's that same plot that we showed earlier that was depicting the 24 hours of maritime traffic using satellite AIS data. And so overlaid here in yellow are all points during 24 hours where we're collecting RO data. And so you can begin to understand how much of a difference these observations are going to make in a forecast when you add them in. Did you want anything, Jack?
No, I mean, well, I mean, the key thing here too with the ship ones is that it's fairly intermittent. Depends where the ships are, I guess, to some extent, versus the satellite ones where you can get it more continuous throughout the day.
Right, exactly. Okay, so how is collecting this data exactly going to improve forecasts, or how is it? Oh, I just wanted to point out here, the increase in data over the oceans is huge, and that covers a whole lot of the gaps we've talked about so far. But in addition, the Spire data here shown on the left compared to the upper air sites on the right-hand side are also increasing coverage over continental areas in remote regions as well. And so that's all very important and factors into the forecast accuracy. Okay, so you, like I've been saying, Spire has been able to fill un and underobserved regions where additional observations are going to have a huge impact on the forecast. And so to that point, on the right here are plots of the 500 millibar temperature surface. And so on the left-hand side is the ECMWF analysis at initialization. And then on the right-hand side is the 168-hour forecasts for starting from the top is the Spire forecast, and then the ECMWF forecast, and then the NOAA operational forecast. And so highlighting, the red circles are all highlighting areas where the Spire forecast is highly accurate to that ECMWF forecast. And this is an important result showing that the positive impacts of Spire RO extend way beyond the surface. Right. So to be fair, that analysis was done internally. So the question is, can that be verified externally? And to that point, shown here on the right is a plot that was created by the ECMWF. And this reflects the impact of and forecast sensitivity to a number of different observation types. And so following the reduction in airline traffic in March, which is shown in the light blue line there, the ECMWF increased the amount of RO that they were assimilating in order to fill that void. And that data signal is shown in the yellow line there. And what I'd like to highlight here is that in this independent analysis, you can clearly see that the RO data provided by Spire had a large additional benefit on their forecast. Sean Healy from the ECMWF, in fact, noted that the addition of Cosmic 2 and Spire RO data decreased forecast error by 13 to 14%. And that conclusion that Spire RO has a positive impact on forecasts is backed up by another independent study that was done by the UK Met Office, where they concluded that assimilating observations from Spire, in addition to the current operational network, had a huge, substantial benefits to their forecast performance. And so these conclusions are, I think, very much in line with what the folks at PredictWind have found when they did their own analysis. And on that note, I'll let Jack take over to review those results in detail.
Okay, thank you. So do I have control or?
Jack, you should have control now.
Not working. Oh,
Yeah.
there we go. Ooh, no.
It's a little laggy.
Too far. Okay, first of all, where are we? Here. Get this some delay here. Okay, so first of all, I'm going to just briefly introduce what PredictWind is. It's a company that's been set up to provide weather forecasts to the sporting and leisure and maritime community around the world with high quality forecasts. So what the PredictWind does is it runs its own in-house proprietary weather prediction models, but also uses forecasts from available high-quality global models as well as other models that's deemed high quality. And they produce this information into a web app that Nick will talk about later, which allows you to do both looking at the forecast, looking at detailed maps of different variables, do routing, departure planning, and get alerts about different conditions, primarily wind conditions. So that's PredictWind. So the next question is, why does PredictWind partnership with Spire? Well, again, Keenan talked about a little bit about this. To get the best weather forecast, you need basically three factors. One is the best initial conditions, which Keenan talked about with what Spire is doing with the satellite RO. The second one is you want a good numerical model, obviously, that has good dynamics, physics, and numerics. And then also you want high resolution to get more detailed. But with weather forecasting, just because you can never sample the air completely, there is always going to be some errors that crop up in any model. And so no model is going to be perfect all the time. So that's why you need a range of models, or what's called ensemble forecast. Provide multiple forecasts, provide the end user some idea of what might happen, and then they can make a decision on how the forecast evolves. So the partnership with Spire is, first of all, as Keenan talked about, Spire can generate the best initial conditions because they have these additional radio occultation observations. And I think he's demonstrated that that definitely helps give you a better starting point for your forecasts. The Spire produces its own forecast based on a well-developed model. They're also one of the higher resolution forecast or finest resolution forecast global predictions available. And additional, of course, from PredictWind, this ensemble question is the multiple forecasts. We'd like to make sure that the end user has those forecasts. Ooh, somebody's controlling it. Okay, so what do we do? Well, we wanted to assess how well the forecasts are doing. So we want to compare the wind observations from stations and to the forecast for the various models to make sure that we are providing accurate information and to give the end user some guidance on how good the models are. So this study I'm going to talk about is based on the 4 global models that we had available. ECMWF forecast, which is sorry, one of the better or world recognized leaders in forecasting around the world. Spire, their forecast using their model and their new observations. The UK Met Office, and what's commonly used, especially in North America, is the GFS forecast. So all these are provided by PredictWind in their app. And what I will show is some of the results from analysis. So this study was a study over 4 months of this year, from February through June. We collected all the data from the various forecasts and the observations. The observations were hourly mostly, out to 7 days. The forecasts could be hourly, or some of them were 3 hourly. And we did look at coastal stations over land as well as buoys. I'll just talk about those observations that were over the buoys, and about 166 buoys were evaluated for this study. Is it clean? No. How come I can't go forward? I don't have control anymore. Does somebody else have control?
There you go, Jack. You should have it.
Still not going anywhere. You would have taken and just, oh, there we go.
Yeah,
Oh,
I'll take it if you want. I don't know what
okay.
happened, sorry.
So what are the results? So here we're comparing the buoy observations against the various forecasts over the open ocean. On the left is the wind speed error, and on the right is the wind direction error. So the measure of error we use here is the mean absolute error. So this is, you take the difference between the forecast and the observation, and you take the absolute value of that, so it's always positive, and then you average it over the day and over the 4 months to get the statistics for each day. So the axis is the forecast day from 1 day out to 7 days, and the vertical axis is the measure of error. The bigger the number, the more error there is. So if you look at wind speed, you can see that typically models on day 1 have errors of 2.5 to 3, growing to day 7 where the errors are up to 4 knots. I'm showing here, which if you want meters per second, it's about 1 meter per second is about 2 knots. So the 4 lines there are the Spires in black, ECMWF in gray, UK Met Office in blue, and GFS in the yellowish color. And you can see that for wind speed, the Spire and ECMWF are very close, with the Spire showing a little bit more improvement, a little less air below ECMWF, which is quite remarkable because, again, ECMWF is one of the world recognized leader in forecasting, global forecasts, and the resolution is very high. So the fact that Spire can actually match and beat ECMWF for wind speed is quite good. And you can see that it actually beats it for all time periods, although very small air differences there. But for wind direction, you can see that actually the Spire forecast actually is remarkably better, about a couple degrees at least, better than the ECMWF, GFS, and UK Met Office. So these results tend to indicate, first of all, that Spire is doing a great job. And I think that's largely to do with because the air is good at day one is largely to do with their better observations that they're using and the good model. But also keep in mind that these are average errors over 4 months. So this is sort of the mean statistics. Any given day, any given model may be best. So you still have to be aware that you can't just use Spire. I mean, although I'm sure Spire people would like you to use their forecast, but again, every given day you have to look at a range of forecasts to actually assess what might actually happen. And that's what PredictWind does.